What is going on, everybody? Welcome to OverKill Projects. So I am in this fun little window because I had previously made this video in one big chunk, but I split it into two parts. So today you're getting part 2 of moving to STM32 via the Nucleo boards. We're going to cover programming the board and getting the LED blinking, all that good stuff. Last time we did the hardware setup and configuration. So if that's what you're here for, check out part 1. I'll put links to it down below, and also probably these like little info box things will pop up somewhere or other and tell you can go over there. So if that's what you're looking for, head over to part 1. But otherwise, let's move on with part 2. I'm super excited to get this thing blinking, so let's get started. We're going to go into core and then source, and then you'll see in there it should say main.c. Now main.c is the main functionality of our code. It's going to be like our home base. So double click on that and that'll take you in. And now it's going to function like, like a sketch in Arduino. So I'm sort of assuming that your background might be in Arduino. If you've seen sketches, then this is like a sketch. Oh yeah, and before I forget, there's these little buttons up here in the upper right. These things are the different perspectives. We are looking at a C file, it contains some C code. So make sure you're in the C++ perspective. Make sure you click on that thing. And once you do, you'll see, we have the normal editor window, but we also have like this nice little outline section over on the right, and then down at the bottom there's like a console and problems thing that'll give you if there's errors, and when you're building code the output will be there. And then next to that, down on the bottom, there is a build analyzer, which is really handy. It'll show you how much memory you're actually using on your device once you do a build. And now if we explore the code that was generated, you're going to see all these things. There's like tons of comments, and a bunch of them say user code. So it'll like say user code, and then it'll have a section, and then it'll say like user code, and then end that section. Okay, so when you put code into this program, you're going to put it into those user code sections. You're going to sandwich it between like the start and end of each of those sections. And what that's going to do is, if you have to go back and make a change to the configuration in CubeMX, as long as your code, the code that you made, is inside, sandwiched between those user code sections, it won't get overwritten. So a whole new, configuration can be written by CubeMX without stepping on any of your code. So make sure to be careful when you're doing, a project using CubeMX. Make sure that you put your code in those user code sections. And now scrolling down a little bit more, we see that there's like this TIM handle type def HTIM2. That's actually our timer 2 structure. It contains all the different timer 2 register configuration stuff that we did from CubeMX. It's all in there. It's ready to go. And that level of encapsulation is pretty great. It's going to be something that you'll see us do ourselves over and over again in our own code, is to take a logical unit like a timer or like a specific peripheral, and you just put all the variables that you want, everything that corresponds to like the registers and all that sort of stuff is going to go in that structure, and then we can just pass that structure to functions as a whole unit, and it makes the code just so much more readable. It's a great device. It's a great way to think about structuring your code. And then we keep going down. We see that there is a main function, and if you're not used to dealing with C, something you should know is that every program needs to have this function. There should be a function that's called main, and it should probably be in a file like this one called main. And what you'll notice is that when we go inside the main function, we're going to see some of the initialization that needs to be done by the system. That's going to be executed by functions that we'll see in a second are down below in this file, and that's part of what CubeMX gave us. But you'll also see that there's going to be this while loop. It just says while 1, and then there's a loop. And if you know anything about programming, then you know that this while loop will always execute because the condition, which is 1, is always true, since true is 1, or at least not 0, and 1 is not 0, so this is always going to execute. So the program flow looks like this. We're going to start at the top of this file and just sort of read down, and there's going to be all this like global stuff that happens before we get to the main function. Then we get to the main function, and now we finally have scopes. In other words, if we put variables inside of main, they're only going to be accessible to main and the things inside of it. And then after running through whatever is in main, when it gets towards the end, we're going to hit this while loop, and then we're just going to sit in this loop forever. So when you plug in this board, it's going to do whatever is in the global scope section above main, then it's going to do whatever's in main, and then it's just going to sit in this loop indefinitely unless there's some sort of error or something that kicks it out of the loop. And so now to associate this to an Arduino sketch, if you put something outside of main, above main in this program, in this file, then that's like a global scoped thing in a sketch. That would be like if you had global variables outside of both the setup and loop functions in an Arduino sketch. The setup area, the setup function in an Arduino sketch is just like the area inside of main, but outside of the loop, above the while loop. And then the while loop would correspond to, in an Arduino sketch, the loop function. This is the thing that's going to be executed over and over and over again. And so you can already kind of see how the Arduino language works. It really takes that C structure, it's sort of built upon C, and just makes it a little bit easier to understand. But this correspondence is one-to-one. It's pretty easy to, if you understand the one, to move to the other. And now if we scroll down a little further, there's going to be a bunch of functions down here. These are the functions that are going to initialize our peripherals, the things that we set up in CubeMX. So you're going to see that there's like the RCC section here, and you should see some stuff that corresponds to the things that we set. You're going to see the timer initialization down here, and you should see like our pre-scaler and our counter interval stuff set in here, and you should see then down below that somewhere the GPIO section, and you should see our GPIO pin PA9 set here with all its various options. And now these are the things that Cube generated for us that we would have had to do manually before we even got this project started. And now this video is already too long, but you can see that it would have to be so much longer if we were going to do this step by step without using CubeMX. Now scrolling up above main again into the global section, I'm going to make two global variables. They are both going to be volatile integers, and I'll get to that in a second. One of them I'm going to call T, and the other one I'm going to call T_old. And I'm going to set both of them, I'm going to initialize both of them to 0. And it's generally a good practice. In fact, it should be the practice, the thing that you do. Anytime that you're going to change a variable in an interrupt, you should make it volatile. The reason for this is that if your interrupt deals with an external stimulus, so maybe somebody pushes a button or something like that where it reads a signal off of one of the pins and then it's going to make a change based on that. The compiler might not understand that that code is ever going to be executed. It might look at that and say, oh well, this is never going to actually be executed, which it wouldn't be if no one ever pushed the button. And so then it might go ahead and compile all that stuff out thinking that it's optimizing your code when really all it's doing is not including the code that you needed. So now we have two tasks left that we need to complete here. The first thing we need to do is to have the timer. Every time the interrupt is triggered from the timer, it needs to increment this variable T. And then I'm going to use that variable T to trigger the actual toggling of the LED of pin PA9. So that's the second part, is the toggling of PA9. And now something that might not seem intuitive if you haven't done this before, especially since we went ahead and configured the timer already, is that the timer isn't started by default. You have to manually start the timer. And to do that, we're going to use the HAL API, the HAL libraries. So HAL stands for Hardware Abstraction Layer, and it is just that. It's a set of APIs. It's a set of functions that are available to you to use that don't tie you down to the specific hardware. And one of the nice things about that is if we program this Blinky using everything that we've done up until now, and we do it all in the HAL libraries, in the HAL API, then if we wanted to move this to a different board, we probably wouldn't have to change anything unless there was some specific hardware that wasn't available, some peripheral that wasn't available on the new microcontroller. So the HAL API makes your code more portable. And this can be a good thing if you haven't really locked down what microcontroller you want to go with yet. But there's also a lot of downside to HAL. It's not very fast because instead of being optimized for the hardware you're working on, it's abstracted away from that, and there are a lot of steps that might execute before you actually get to the thing that you're trying to execute. And all those wasted clock cycles can really add up when you're working on embedded hardware. And so you'll see a lot of people online just throwing all kinds of shade at the HAL layer, the HAL libraries, and saying, oh my God, you should just, program right on the registers. You should just do bare metal, make sure you do it by the registers, blah, 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 blah. And that's all well and good. And I actually kind of endorse that myself. And as we move along, we will get closer and closer to doing that. But when we're just starting out, it's so much easier to use the tools that are available to you. We're sort of making a jump from Arduino, which already abstracts away from the hardware, so you're already used to that world. So we're gonna stick with this for today with the Blinky, and then we'll slowly move away from it as we move forward. And I think really the biggest benefit of moving away from HAL is that it makes you read the datasheet for your microcontroller and understand what that thing is really doing under the hood. But now, how do you know how to use the HAL API? Well, there's a lot of different ways to go about this. You can try to sort of browse around online, but I find that the easiest way to find the stuff that you're looking for is to actually go right to the code. So you'll see that there's this little drivers folder down here in your Project Explorer. I'm gonna drop that down. We're gonna take a look at actual source code. So we're gonna drop down source. Then you're gonna look for the thing that says TIM. You're gonna double click on that. It's gonna open this thing. It's gonna ask you if you wanna do scalability mode if you haven't done this before. I want it to not take away my outline over on the side. So, I'm gonna make a quick change and then apply, okay. And now I have the code and I have all the functions listed out on the right. And you can see in here some functions that you might have noticed before. So there's like the HAL timer base initialize function that I think was actually used in the MX timer initialize function in our main code. But what we're looking for here is we want something that's going to start the clock, and we want it to start it in interrupt mode. And so sure enough, there is a function that is HAL timer base start int. And that's exactly what we're looking for, or IT rather. Okay, so this is going to be the function that we're going to go ahead and call in order to get the timer started. So going back to our main code, we're going to go ahead and put a line in that initializes the timer by actually starting it. So we see that there's the MX timer initialize. We have to do it after that because otherwise the timer won't be initialized, so we want it initialized. So then after that line, we're going to go ahead and in a user code block, of course, we're going to put, HAL timer base start IT, and then we're gonna put our HTM32 struct in there, and that should start our timer. So now we're gonna have this timer and it's going to count up, and like I said, we're gonna see that we're gonna make it increment the T variable. So now I'm gonna use that T variable to actually toggle the LED. I'm gonna do that in the loop. So every time we go through the loop, it's going to check to ask, is T greater than T old? Or actually, instead of greater than, why don't we say, is T not equal to T old? If it's not equal to T old, then we can go ahead and assume that it must have been incremented. And so now in here is where I'm going to put the toggle function. And just like before, maybe I don't know the HAL layer enough to do this, so I'm gonna go over to the HAL drivers. I'm gonna find the GPIO file. I'm gonna open that up, and then I'm gonna look for something that seems to be named something like what I'm looking for here. And in this case, it's easy. There's a HAL GPIO toggle function, and that's what I'm going to use. So now I'm gonna go ahead and include that in my loop, in my conditional statement, in my if statement, and boom, there we go. Now every time T is not equal to T old, we're going to toggle our pin. So now how do we actually increment T? How do we deal with interrupts here? You might be used to doing like an ISR function somewhere in here, and it'll hit that every time or whatever. But in this case, there's actually an entirely separate file that handles all the interrupt stuff. You'll find it over here in the Project Explorer. It's gonna have this little IT tag on it. So you double click that, open it up, and now you have this new, file that has a whole bunch of nonsense in it, most of which you aren't going to need. But something we are going to need to do is we're going to need to expose the variable T to this file. And to do that, we're going to use the extern keyword. So I'm going to come down here to where I have the user code, private variables, and I'm going to do extern int T. And what that's going to do, since main.h is included in this file, it has access to the global variables from main. One of the global variables in there is T. So this is saying go externally to one of the other files you have access to and look for integer T. And so now that I've put that in there, I can use T in this file and it'll recognize it, and we can change it, and it should change accordingly, and everything should work out great. So now if we scroll down to the bottom, ignoring all the other functions, when you get to the bottom, you see that there's this chunk here that, it says peripheral interrupt handlers, and you'll notice that there's nothing in here. And that's because I forgot to click the interrupt checkbox when we were doing CubeMX. So now we're gonna go back to CubeMX real quick. We're gonna change perspectives, and then we're gonna go down to timer 2. And in timer 2, there was this little NVIC tab that I didn't click. I'm gonna click there, and you're gonna see external interrupts. There'll be a little checkbox. I'm gonna click that checkbox. I'm gonna save this file. It's gonna regenerate code. And now, since we were smart enough to put all our code between the user code blocks, nothing's gonna get stepped on. It should all still be there when it generates this new code. And so we go in, and sure enough, we see everything's fine. We're gonna scroll back down to the bottom of that file, and we'll see down there that now there is in fact a function, and that function is going to be TIM2 IRQ handler. So that is the IRQ handler for timer 2. You'll notice that there's only one thing in there, and it's a call to a HAL function. It's HAL timer IRQ handler. And now that function goes through all these different scenarios and hits different callback functions for different interrupt scenarios. So the interrupts for this timer can be triggered by many different sources. One of them happens to be that the period, the counter interval that we set earlier, has elapsed. That's just one of them. But you can see in here that there's, maybe dozens of different ways that this thing can be triggered, or that different callbacks can be called. But the one that we're looking for is the period elapsed callback. Every time the period elapses, every time this thing counts up to 1,000, which is, what we had it do, we'll go in here, and then it's going to call that callback function, which is called HAL _ TIM _ period elapsed callback. So now that's what we're going to put into our interrupt file in order to make sure that that gets called. And now all the callbacks that were in there are actually weakly defined functions, which is a whole thing that I'm not going to get into, but the idea here is that we actually have to make that function. So I'm going to go ahead and I'm going to make a function that's called HAL TIM period elapsed callback. It's going to take a TIM handle type def struct as its input, and then it is going to go ahead and just increment T. It's going to just put T++ in here, and so every time this gets hit, it's just going to increment T by 1. And now going back to our main loop, we look at what we had there, and now every time this loop executes, it's going to be looking to see if T has incremented. And if it has, and it's different from T old, then it should go in and execute the stuff in there, which is the LED thing. But wait a minute, you might have noticed that I never reset T old. So what I should have in here is I should have at the bottom, I should say set T old equal to T. And now what that'll do is that'll make sure that the toggle function only runs when the interrupt is triggered, only the first loop after that, and then it won't execute for all the other loops until that interrupt gets triggered again. Then it'll do it once, and then it'll wait, and it'll do it once, and then it'll wait, and that's exactly what we want. We want it to wait for those half a second intervals in between. But we're not going to put that in there because I want something to be in there so that we can debug something as we step through this. So now let's go ahead and build this code and see what happens. And so you go up to project and build all, and of course we're gonna have an error because I forgot that we should be passing our struct by reference and not directly. So what we need to do is we need to add an ampersand before HTIM2 when we start our timer. And what that does is instead of passing the struct to the function, it actually passes a pointer to the struct to the function. And that has all of its own things, but this is not a C tutorial, so don't worry about that if you don't understand it, but just know that that is a thing that might happen from time to time, yeah. And I guess maybe at some point, if there's a bunch of questions about it somewhere, I'll make a quick little tutorial that answers why we have that thing in there. But anyway, now if we go ahead and we build it again, we see that it's fixed, it built properly, and now we have down in the build analyzer, you can see there's like a little bit of information about the build we just had. You can see that we're only using about 5% of the RAM on this thing and only about 6.5% of the flash memory. So we've got tons of room beyond that. And actually a lot of that space is taken up by the initialization stuff that we didn't even add. So if if we make little changes, we'll see that we will, for the most part, affect that number very little. And now in order to debug, we're gonna go up to the little bug and we're gonna click on that little drop down arrow there, and there's a debug as, and now that's gonna call up a whole new screen full of stuff. And you should browse around this and kind of look, but you're not gonna need to change anything here. It's gonna be pointing to the right location for your binary if you didn't, set up your project different from the normal. And then, if you click on the actual debugger, the tool, then it should have all the stuff in there for that too. But we're not going to change anything. Go ahead and, say apply and close or hit OK, whatever it is. And then what'll happen is you're going to see that it's going to ask you again, do you want to change perspectives? And now this is the debug perspective. You're going to say OK, and then it's just going to sit there on the first line. It's going to highlight hal_init in green, and nothing's going to happen. So now if we hit the play button, it's going to actually execute the code, and that'll take us down into our loop because we have no breakpoint set. So you hit that play button, then you see that your LED, it looks kind of lit, but that's only because it is literally toggling, I don't know, thousands and thousands of times a second, which makes it look like it's on to you because it's, it's happening so fast. But that's okay. We can go ahead and hit the pause button, and that should take us into our while loop. There's a pretty good chance that that's where you're sitting anyway. If it's not, then browse over there. We can insert a breakpoint at the if statement in order to, check the different variables at this point. And now there are tons of things you can do in this debugger, and they're all so helpful. And at first we'll only look at a few of them, but as we move further and further, we will undoubtedly have to use more and more. Some of the cool things are you can hover over different variables and they'll show you what the variable values are. There's this whole pane on the right that has a ton of stuff. Right now, it's not showing any of my variables, but I can go over to expressions. I can add expressions like t and t_old, and it'll show me what those values are. Then there's a little tab there to check out what the values of all the registers are. There's a little tab next to that that tells you all the different configuration registers that are available on this microcontroller. So like for instance, if we go into GPIOA, we can check the mode R register, and we'll see that like mode R9 is equal to 1 because pin PA9 is set to be an output pin. You could also go through all these different things and make sure that they're set correctly. This is a great tool to have, like when you do a configuration and you're not entirely sure if you did it right. It gives you a way to go back and make sure that it matches what you think it should have been based on what you read in the data sheet. So now if we go ahead and hit the little play pause looking button at the top, we'll see that it'll go around and then stop again at our breakpoint. We see that T increments, but T old does not. This is why that code is not being executed properly. It executes every single loop instead of just the first loop after every interrupt. So we're gonna go ahead and hit the stop button. Then we can go down to that part of our code. We can put in a statement that will make T old equal to T after we toggle the LED. And now that will prevent the behavior that we were seeing before. Now we can go ahead and run this again. So we go into the debugger, we're here again, and now it's the same sort of thing. We still have the same breakpoint as before, so when we hit play, it's going to stop. And we can see, we hit play and we see both numbers toggle now. We should also see the LED lighting on and off. That's exactly what we wanted to see. We can remove the breakpoint, we can hit play, and bingo. Now the thing is lighting just like we wanted, on and off every half second. Whew. And we're done. So now if you go ahead and you hit the stop button, it'll just keep running. We'll see the LED keep going on and off. And that's because now this is the code that is loaded into the microcontroller. And so every time you plug it in, it's going to run this program unless you specifically are running the debugger. Whew, and there we go. That was way longer than I wanted to take, but everything's working. We got our little LED blinking. Everybody loves a blinky, and hopefully now you can go ahead and set this up yourself and make it work to light an LED, but you should also sort of have a good idea the direction you would take to make the microcontroller do other things and make the Nucleo board work a lot like an Arduino. I hope you learned something today, or were at least entertained. If you were either, hit me with a thumbs up down below, subscribe, the alert bell, all that sort of stuff. Check the description for links to all the stuff that we looked at here. There was way too much, so it'll all be listed down there. Leave a comment if you want, and that'll do it till next time. Thanks for joining me.